We want to talk our way through a new situation and a new distribution today. We've mentioned several times that there will be cases when we're interested in knowing about the variance of population A as compared to the variance of population B. Now, what we're going to do today is fairly restricted. We want to start with two populations that are normal, and so the populations, I'm going to call that the POPs, are normal. And in addition, we want to be using independent samples. Now let's suppose that we're sampling men and women's blood pressure, systolic blood pressure in particular. And so a hypothesis might be that the variation, the variance, for women's blood pressure and men's blood pressure are not the same. So we might be talking about sigma squared, I'll say W for women, is not equal to sigma squared M for men, that their variation, the variance in their blood pressure is either equal, or we might be talking about not equal, or we might be talking about one greater than the other. What we would have to do is to find a statistic, and remember the definition of statistic. It was something calculated from a sample. Calculated from sample. In this case, that'd be plural because I've got two samples, two independent samples. So the statistic is calculated from a sample. It needs to tell me something about what I'm investigating, something about these variances. And of course, I'm going to have to know the probability distribution for that statistic also, because I'm going to have to calculate the probability of it being greater than or less than or equal to. Now, with a little thought, you might come up with this, but let's just suppose we're talking about systolic blood pressure for women versus men, and there's a claim that sigma squared W is not equal to sigma square M. That's a claim that some researcher is making. Of course, we know already that this is going to have to be a claim in a null hypothesis because it does not contain equal, and the thing that would stand in position, the thing that would stand in opposition, would be W squared equal sigma W squared equals sigma M squared. So these two exhaust all possibilities, and so there's a pair of hypotheses. Well, what about a statistic? Well, the statistic that comes to mind would be, maybe I would look at S squared W. That would be the sample variance that I would compute from my sample of women. And what if I would look at S squared M, the variance from the males? If in fact the two sigmas are equal, then I would think that this ratio should be approximately equal to 1. That would indicate the sigmas are equal. And if the ratio is greatly different from 1, either a lot bigger than 1, meaning that this numerator term is bigger than the denominator, or much, much smaller than 1, meaning the denominator term is much bigger than the numerator term, well, in either of those events, it would not look like sigma squared W is equal to sigma square M. These are the sample variance and the population variance. And I would expect, if I have a randomly chosen sample from a normal population, that S squared W would be a good estimate of sigma squared W, and the same for S squared M. Now, I would need to know the probability distribution for this statistic right here, because if I took my samples and computed S squared, I want the W here, S squared W over S square M. If I computed that for a particular sample, I might put the little asterisk on it, has been our habit in the past, to indicate that that's observed value. Then for all the possible values of S squared W over S square M, I'd like to know what's the probability that S squared W over S squared M as a random variable is greater than what I observed. And that's the value that we've called P in the past. And this is the one that would be compared to alpha to complete a test of hypothesis. Well, we're in luck because I do know the distribution of that statistic that I've written right here. I do know the distribution of these ratios of sample variances. And the name of this distribution is the F distribution. We use a capital F to indicate that distribution. Now, I'll tell you several things about the F distribution. Let me draw a horizontal axis. The F distribution looks like, it's not identical to, but it looks like a chi-square. And it's got a distribution that's non-negative. It starts at 0 and it runs out to the right. Because the long tail of this distribution points to the right, we say that it's skewed right. It's a non-symmetrical distribution. Most of the probability is down here on the left-hand end, and the distribution asymptotically approaches the horizontal axis on the right, meaning that things over here become less and less and less probable as our independent variable increases. So this would be one of a member of a family of F distributions. Now we're used to families of distributions. Chi-square comes from a family. T comes from a family. Well, F also comes from a family. And we're going to use the concept of degrees of freedom again to indicate which member of the family we're talking about. Now let's concentrate on S squared W over S squared male. This is a ratio, and I take this value in the numerator, calculated from one sample, from an independent sample. I've got the value in the denominator, and that ratio is distributed F. The parameters I need to indicate which F distribution I'm talking about, we're going to call df n for numerator, and there's a second one this time, df d for denominator. So in order to index an F distribution, I'm going to have two degrees of freedom numerator and the degrees of freedom denominator. And the degrees of freedom numerator, dfn for numerator, thing on top, is equal to the number of items in the sample that's represented here in the numerator, in this case the sample of women, and then less 1. And degrees of freedom for the sample on the bottom, denominator, is the number of items in that sample less 1. So those are pretty easy. Now if we're going to be testing here and using a classical approach, just to get some background and get some practice using the F distribution, I would tell you if we have an upper tail test that there will be a critical value, which we're going to have to find, and that critical value cuts off an area of alpha in the upper tail. And we use alphas like we have before with typical values of 0.05, 0.025, 0.01. There's other values we could use, but those are my typical values. Critical value cuts an area of alpha in the upper tail. Now how do I find the critical values? Well, probably the easiest way to find critical values would be to use a table of critical values for the F. I'm hesitating here because I see that I've written off the page, but I pronounced that as I wrote it down, so I don't think you'll have any trouble remembering that the degrees of freedom denominator would be the number of items in the denominator sample less 1. Okay, now let's get back to the F and critical values. Critical values of F. To find the critical value, we enter the F table, which is in the tables in the back of our textbook. This is one corner of such a table. And across the top, our degrees of freedom numerator. And down the side, I'm not so good at writing sideways or I guess sideways you could call it, degrees of freedom denominator. So I'm going to abbreviate like that. Now suppose that what we want is a critical value, and let's just further suppose that for this experiment here, the blood pressure experiment, suppose that we have 15 what's on top? Women. 15 women in the sample and 7 men. And then I'm going to be looking at in numerator, the number of things in the numerator, as 15. I said 15 things in the numerator and put it there by degrees of freedom, so I hope that's not going to cause a confusion. The number of items represented by the numerator is 15. The number of items represented by the denominator is 7. And then my degrees of freedom numerator would be 14. And my degrees of freedom denominator would be 6. To find a critical value for an alpha level of, let's say, 0.5, I would find a table of critical values for F with alpha equal to 0.5, and this whole table will be about equal to alpha equal to 0.5. Across the top, degrees of freedom numerator, I would look until I found 14. Then down the side, degrees of freedom denominator, I would look until I found 6. And then, as usual, I would look for an intersection of the row and the column that I'm after, and this would be my critical value represented in that rectangle. It's important to know two other things about these tables. There are 3 tables of F in your textbook. The first is for alpha equal to 0.5. Now, in the past we built tables where we would have an alpha value across the top and degrees of freedom vertically. But here I have 2 degrees of freedom. So my vertical column is taken up with one of my degrees of freedom. My horizontal column is taken up with the second degrees of freedom. And so where am I going to put alpha? Well, I'm going to let the entire table represent a given value of alpha equal 0.5. If you would flip the page, you would see that we've got a second table for alpha equal 0.25, and then flip again, we've got a whole table for alpha equals to 0.01. So we have 3 tables of the F. You've got to be sure that you've got the alpha that you're asked to use. Be sure you're using the right table. Another thing to know is that we've looked up, I didn't give you a number here, but we've looked up a critical value for alpha equal 0.5 when F has got this number degrees of freedom numerator, this number degrees of freedom denominator. But if we were to turn those numbers around, 6 and 14, if we were to make a mistake and get those reversed, then we would look right here in the table to find the critical value, and these two would not be the same. So the degrees of freedom are not interchangeable. Numerator means numerator, denominator means denominator. I see that we've exhausted almost 15 minutes, and so I think it's time to stop this, and I'll have to do a second video. So for now, thank you.